We're now going to discuss the limit of a function that has two independent variables. And before we get started, we're going to recall how the discussion of limits went in Calculus 1 when there was only one independent variable. In Calc 1, when we had a function y is equal to f of x, if we wanted to show that the limit existed at a particular domain element, because the domain was only one dimension, we could only approach that domain element from the right and from the left. If the y values on the function were approaching the same y value as the x approached a from the right, as we did when x approached a from the left, then we would say that that limit exists. So let's say that that output value, the y value that we're approaching is L. That definition in a two-dimensional function said if we were approaching a from the right on this function and approaching a from the left on this function, and from both directions it appears that the y value that we're approaching is the same y value, then that limit is going to exist and it's going to be that y value L. Essentially, there are only two directions from which we could approach that domain element if the domain was a one-dimensional domain. But let's now consider a surface function with two independent variables. A surface with two independent variables is going to have a domain that is two-dimensional. So if we wanted to try to determine if the limit existed at a particular domain element, and if we want to show that that limit is actually a particular output value, or a z value, in this case again calling it L, we would need to show that as we approach this domain element from actually any direction, that all of these surface function range elements or output values are going to also approach this same limit value that we're calling L. Now this can prove to be a little tricky because we have infinitely many directions from which we can approach this domain element, as opposed to the Calc 1 version that we saw a moment ago. So proving that a limit actually exists can be pretty tricky because we would, in theory, have to approach this domain element from infinitely many different directions in order to demonstrate that those output values are all going to the same place. So proving that a limit exists, we would need to use what is called the precise definition of a limit, which can be quite tedious. It's a lot easier to prove that a limit does not exist. In order to prove that a limit does not exist, what we would need to do is to find two paths that we can approach this domain element from, where those paths generate different limits. So up here on our concept drawing, if we can say that from one approach, our y values approach one output value, but if I come from a different approach path, I'm going to change my graph a little bit here, it's pretty tricky to demonstrate, but if we were coming from a different approach path and we approached a different limit, let's say L1 and L2, and these values are not the same, then we would say that the limit does not exist at this domain element. There are some common paths of approach that can be used that usually are enough to demonstrate that a limit does not exist, but that's what we would need to do, find two different paths that generate two different limits.